Hello. Welcome to Advent of Code. Today will be day 18. I was trying to finish up day 17. So one of the mistakes I made on stream is assuming that the cycle had to be uh, a multiple of our input size, but that's not true because the wind blows an unpredictable number of times per block. And so I had to put in some integers to track where in the original input are we, which annoys me. But then with that, we could build a key. And the other thing I did about yesterday is like, how many rows do we need to make sure it behaves the same? And so I looked. I must admit, I looked at the thingy, the Reddit forum, and people just picked a random number. So, and with that, we can find duplicates. So here's an example of a cycle of length 35 starting at the 26th element of the example. And so what I'm trying to finish up is doing the modular arithmetic to figure out where we need to start and all that. So I'm not sure I've got it right. So one of the problems is there's an inherent sort of off by one problem in that, you know what? I'm just going to fix that. I'm going to fix that right now. All right. No more off by one problem. State 0 is 0 rocks dropped. State 1 is 1 rock. Offset 1 is 1 rocks drop. 1 rock dropped. All right. So let's get rid of this. So we want to find the point after the start of our cycle that is aligned with our goal. So we got that. We go forward until we're, is this true? So what we want is I equals C start, I equals goal mod clen. I'm having trouble justifying this. This should be an easy problem, but it's one I always have to work through carefully to make sure I'm not fooling myself. So if the yes, so C start mod clen and minus start mod clen cancel each other out, and we're left with goal. All right, good. So we calculate So calculate white height. Height, we are there. We show how much height we add for each time through the cycle. So solution should be so we take goal minus I divided by the cycle length and multiply by delta. All right, let's try this out. Tops, I keep typing sock, top, rock. The only thing I'm worried about is one of the people that commented we might have to ensure that we've gotten all the way through the wind at least once, which we can do. Just a complication. All right, does that look like the number 1514285714288? Yes. Hurrah. All right, let's try to solve the real problem. Amazing. Hurrah. So I'm curious what position we're at here. 9600. Okay. I mean, we done worse. We got it. All right, time for today's problems. I love the little ASCII art volcano here. This looks like the map from a mud with a, a world. You know, I actually contributed some code to one of those. Had a little ASCII art map you could go between regions. Or Caves of Cod. You can go play that with its ASCII-ish world map. Okay. Number of sides of each cube that are not immediately connected to another cube. All right. Good. We can do this. I'm worried about part 2, but all right. So let's do our bookkeeping. We need to switch to day 18. All right, so we've got a cube that's got an X position, a Y position. See, they're in that order, correct? Given as it's okay. Okay, we need to give a constructor name. Kubelet. There's a fancy name here. The name is Voxel. There we go. So let's. You may not need this, but I figured I would just get it out of the way right away. Okay. Let's copy that data type into specification language. In case I haven't mentioned it today yet, I'm not just using Haskell, I'm using Liquid Haskell, which adds refinement types to the base Haskell language. I don't, there shouldn't be any restrictions on that, so let's parse the input. We're going to use our favorite split function. Okay, so let tokens equal split by, is it split by one of? I could be using split on, I guess. So I've been using split one of, but split on would let us use an arbitrary string. Sure, split on comma s. So if length tokens does not equal 3, then something went wrong. Else point just a point. Okay, good. So we're going to count the number of exposed faces. So we're going to need a set or other container. Okay, so count exposed. So we're going to write a function that takes the set of voxels and counts the number of exposed edges on one of them. So set dot from list. Our voxels go into set, that goes into our function, we run it over the list again. Exposed in all right, so what do we need? We need the neighbors of a voxel. So it has one for each face. And oh, this is a list. And so let's specify that this list had better contain 6 elements. I know, here's a handy cube. It's not always a cube, it comes apart to other shapes, but it's a cube now. And we can easily count 2 on top, 4 around, so that's 6. Okay. So we didn't write an add function like we had for coordinate. So I'm just going to do this in you know what? All right. We're going to define Manhattan distance. Where did we have to do this before? looks like this is all liquid Haskell output. Somewhere up here, there should be a file name day 15. So take the absolute distance measure we got. Equals. All right, now we have the Manhattan distance as in our specification language, so we can say every neighbor voxel has to be within phi n equals 1. Exactly. So that's a pretty comprehensive definition. So the actual writing of this will be boring, which is why I've been procrastinating. All right. Gonna hide the old absolute value. Okay, so does it? Oh, wow, it did not like. It did not like our Manhattan distance. I guess it looks like we had the same problem before. I'm gonna leave a note here. It would have worked a lot better if I had typed correctly. Okay. Oh, all right. So we do have to define order. Oh no. We have to have an order in order to use it in a set. What's the next problem? Still catching up, I think. All right, good. It believed our neighbor function specification matched what we actually did. Good. So given that, we just have to we want to count how many of those neighbors are in the set. So we're going to map, we're going to take the length of the filtered lists, and we're going to filter the voxel by set dot member v in S. Neighbors of v. All right, that's not too bad for an inline function. Could we give it a specification? So the problem is that sets don't have a size in the model as in the specification language as currently defined. If we open up there's no set that gives a size. We can do emptiness. The size method isn't even given a specification here. So that's a little frustrating. I was working a little bit on could we do a better job of, well, that was on map. So which is unfortunate because Liquid Haskell uses SMT solver, it's Z3 specifically, as the backend for checking all the things we tell it are true, which is now how it knows how to do arithmetic, and Z3 understands sets as well. And so this is a mapping of sort of, there's a mapping onto Z3's set theory, but not one that lets us take the size of a list. So there's a list elements measure. So could we say, oh no, that moves from a list to a set. This moves from a list to a set. We want the opposite. We want from a set to a list, which we ain't got. All right. It's unfortunate because that's sort of the key thing, and it doesn't look like we can prove its correctness without adding a bunch to the language. All right, let's put it to the test. So I'm going to use map maybe, for which I need data.maybe. So let voxels equals map maybe parse voxel on our input. Great. Okay. I think that's it. Doesn't feels easy after yesterday. Guess it is a Monday puzzle. Well, that didn't work at all. Oh, did I? No. So I may have didn't been trying to do the bounding. Okay, yeah, expose. So this needs to be not member. Okay. I mean, we could all do this all in terms of lists, but my input may have been bogus. Did I? Yeah, I loaded day 17s. Didn't save. Should be 64. All right. Let's get our real input. Okay, I hope we get it all. That's the right answer. All right. Yeah, so we need exterior surface area, which is a significantly harder problem. So, well, okay. So, first idea is we could project a line out of each edge to infinity and see uh, whether anything was on that line. But that just tells us that there's something there. It doesn't tell us whether we're inside or outside. So what we have to do is find completely enclosed points in 3 dimensions. Okay. Uh, we can do this. So we can use union find. Um, right. So we've got bounds. Uh, okay. So we can compute bounds for how much the area we're looking for is. And then we can calculate the connected component for every region in that space, whether it's outside, rock, rock, magma, whatever it is, or an interior point. And then we can go over the set of interior points and calculate. Well, we can either do our computation again and treat the interior as part of what we don't want to as not being exposed, or we could add and then subtract to sort of inclusion exclusion. All right, so let's get some bounds. Is there a simpler way? Well, we could just do depth first search. I mean, DFS works fine too for finding the connected components. Maybe we should do that. I like Union Find though. It's cool. Well, we've already got the neighbors for doing DFS, although we need that for whatever we do. Um, all right, we're gonna need the bounds whatever we do. So isn't that a lovely data type? So we could put a specification here. We could say that this integer is less than or equal to the y coordinate of any. No, we can't. So this is also a side project I've been working on, is how do we define minimum? And I don't think we can define it as a type. We'd have to prove it as a theorem. All right. I'm just going to look at this number. Okay. Max x minus min x times max y minus. So I'm calculating the volume. If this number is large, we may have to think again. Looked like it was sort of. Oops. Looks like it was in the feasible range, like 4,000. Come on, what's going on? Max. Precedence issues. Functions bind more tightly than uh, mathematical operators, which matches real life too. Yeah, so we only got 9,000 points to work with. Not a problem. All right, let's do depth first search. So we're going to give it a set. Let's be smart about this. So we're going to want to do some DFS is for uh we're going to want to do some DFS for regions that have rocks and some DFS for regions that don't have rocks. And so the easiest way to do that is give it a predicate. Is this voxel connected to the one you care about? So we can give this a better name. So again, we give it a voxel. We're going to give it bounds. That's what we need. Do I have to define a type for these bounds? I think I do. All right. So we've got are these two connected so that either both be in a set or both not be in a set. I'm wondering whether you should make that take both arguments. Generate a neighborhood and starting point. Okay. All right, we're going to use a helper that we'll call DFS. Take the same arguments, but also a pair of empty sets for what we've visited already and the thing that we're building. Proving termination for this might be hard. Because again, we don't have the notion of the size of a set, right? We could say something like, there are only finitely many values, although we didn't pass those in, and the set is growing up towards that. So eventually, they must meet or we terminate. So let's. Is there any way we're going to be able to prove termination other than doing everything with lists, which I hate? I'm not seeing it. Really nice if we. We could give it a count and a maximum. And then we just have to be careful about only recursing to a neighbor if we've never seen it before. All right, I think we're just going to ignore the problem, although that pains me. Okay. So we're going to visit we can just do both these together. That can just live inside the function. All right, so we've got currented, visited, and our connected set. So new visited equals visited union. Okay. Visited and connected are the same thing. Are they? Are they really? I may not be thinking about this like a functional programmer. So if it's in Python, I just pass a set around, and we'd update that set whenever we visited something, and then whatever branch of the tree we're in, it's fine. So I think we'd have to. If we want to do that, then we have to explicitly create our queue, or else we have to pass in one branch's visited set into another branch of our recursion. I mean, which is what the Python-esque solution would do anyway. Sure, so let's do a queue. All right, so the base case, we don't need a queue. We don't need a current. So we got the neighbor generation set, our connected component, which is all the ones we visited, and our queue of ones to visit. Okay. So an empty queue, then we just return visited. Otherwise, visit it, ask for its neighbors, filter those by those we haven't already visited. Not set.member and visited. Or new visited, I guess, would be more consistent, but nothing should be a neighbor of itself anyway. Okay, and then we're going to recurse new visited, and the queue is going to be n2 plus appended onto the front of our list. That is what makes it DFS, is we append on the front instead of on the end. Union. Okay. Why isn't Liquid Haskell yelling at us about this function not terminating? I'm very confused because I bet it's all hidden here. I bet that's what it's telling us is, hey, I assigned to your program a bunch of false types because you didn't use these, and the only way. All right. So let's write the neighbor generation function. So it's going to, we need both. Okay. Okay, so we're going to take the input set, and we're going to take voxel, and we're going to compute the bounds. It really feels like we should be defining a type for this. All right. All right. So there's the rocks, bounds. So the starting rock, the starting position, and the voxel v. Okay, so we want all the neighbors, all the, yeah, this is a bad name, but at least it's distinct. So we want to take the neighbors of V, and we're going to filter them based on, is it in the same class as the start point, and is it within bounds? So same material. It's either inside or outside. inbounds of x, min x less than or equal to x, and x less than max x, and same for y. Okay. So if set.member, so this is true if they're either both which direction does this go? They're either both in the set or both not in the set. All right, so we can write at least a partial specification here. I'm not sure we can do this though. This might not be legal. All right, so this returns a list of voxels, and every one of those voxels had better be Manhattan distance 1, and xcord v2, which is the same thing again. All right, does it understand that at all? Yeah, it really doesn't like that. Okay, so we could unpack them all in separate arguments. We could define a data type. We could give up on writing specification too, but hey, we're using liquid Haskell. So is there a way to do this that is not too painful? Okay, we just entered the land of kind of painful. I don't. And kind of gross. All right, but we can write an inbounds function. Uh, I think I want to use this as an inline function, so I'm gonna do it. I'm gonna use all the accessors here. Instead of unpacking things. Okay. So we can just change this to inbounds. All right, so let's change this to a bounds object. And call the same function, which is kind of cheesy. Okay, so this is interesting, that it doesn't believe us. So what part of it doesn't it believe? Like this should give us half of it. All right, let's try just this. Okay. So it's definitely the part. Let's clear up the variables here. All right, so we didn't give it a type. I would have thought the type of, the type would have been implicit here. Here's what I'm going to do. We're going to use inbounds for the specification language. I don't think this will work. Okay, good. So that gets this into the specification language, which I'm worried that this inline did not. So if we call check bounds, does that make it happy? No. Match. All right. It's causing problems here. So I don't know what else we can do except sort of maybe inline the check, which seems ridiculous. Um, I'm going to put a Okay, just verifying that that should check out now. Yeah. So we got carried through neighbors. Wonder if it's the wonder if it's not inferring the right type on this lambda. Um, what if we split it out? No. Okay, well, all right. So what I'm going to try is I'm going to do set mem of can we put our other part of the condition in here? Have it checked. No. That also failed. All right, let's try let me look at the type. Oh, I bet I know. All right, I've made this mistake with f star a bunch too. Is I gave it too much credit. Right. So if you look at the type there for filter, it preserves the type of the original list, but it doesn't introduce any new type information. Right. So it should be that can we give a better specification? No. So it doesn't like that we tried to call f. We might need to in order higher order functions. All right, well that's disappointing. So we could write our own version of filter that did that. But that would be a little silly. So we won't do that unless we really need those properties later. All right. So we've got find connected component. We wrote the input it needs. It's going to give us a bunch of. It's going to give us a set that's a component. Um, all right. So we need to identify the outside and. Do we need to identify the outside? I guess not. We need to identify. All right. So the rock fragments are our input. We want to identify anything else in the region that is uh, inside the rock, but not, the surrounding air. So I guess to do that, we need to. Okay. So we're going to take our input set and our bounds, and we're going to return the things that are inside. So the first thing we need to do is figure out which the points inside our region are actually outside. And the easiest way is do DFS starting from a point on the boundary that's not in the rock. Okay. So one way we could do that is make the bounds slightly bigger and select a point on that. I think that's the least painful way. Otherwise, we need to, the way we defined it is the region is right up against the min and the max. So if our rock's shaped right, it could actually cut the outside into multiple spaces, which is super painful. Um, so we're gonna create a slightly bigger region. We'll write this as a function. That wasn't actually very helpful. All right, so that gives a box two bigger in each coordinate. So that's guaranteed to completely surround our rocks. Okay, so the outside is the connected component. that's based on the neighbors of the looser bounds and the point that's all right. Min x looser bounds min y. Okay. So we want the points that are okay. So we're starting our search outside the initial bounds. We're looking for ones that are also not in rocks. Okay, that should be our set of outside coordinates. So the ones that we have to search is, okay, let's do, set from list. So we're going to take all the points in our original bounds. So x, heck, let's write this as a function too. So this is sort of the, it's a pseudo inverse of bounds, right? Bounds of all, it's a left inverse or a right inverse. It's one of the, not a true inverse, but a one-sided inverse. Okay, point x, y, z. So x goes between min x, b, and max. Okay, just list comprehension. Okay, so the search space is going to be all bounds, all the points that are not connected to infinity, that are not outside air. All points. Right, so there may be multiple connected components in there. So we're going to have to take them out one at a time and decrease our set. So I'm having trouble coming up with the name. I'm going to switch this to a where clause. So we're going to explore Okay, so this is going to take set of voxels yet to be categorized. I guess we only need one set. All right, so so if we've completely exhausted the search space, then we're done. Great. Start. We need to extract a single element from a set. Is there a helper to do that? Data.set. Oh, that's the wrong one. Oh no, I guess it's fine. Remember lookup. Aha. We can take the minimum. Okay. So we'll find the connected component there. So we're going to use the original bounds. That repeated argument looked kind of dumb, but okay. So if, and then we're going to recurse. So we're going to call Explorer, and we're going to remove the connected component from our search space, and then if it's a rock, it's not a rock, member start v rocks. We can skip that out. We're gonna have to do both cases. Else on rocks union. All right, so we always remove it. I have a bad habit of pluralizing the type names. Yeah, termination error. Does this work? Can I just tell it, yeah, it might not terminate. Or do I have to turn it off entirely? Okay. Bounds. All right, let's just check this again. So extract a position we haven't searched yet, find the connected component. If our start set was a rock, then everything else we got is rocks too. Otherwise, the connected component is non-rock spaces. Okay. So I think that's all we need. Because once we have all the interior voxels, we can just call count all right. I guess we do need to update that. All right, so we're going to take the bounds. I kind of don't want to do all this together. given the list, the rocks and the non-rocks count exposed faces not in either set. Okay. So this is just rocks, union, interior. Set. All right. So we're gonna do the work out here. We're going to say let's not build the same list twice. Two voxels, so rock set and the region. Um, I kind of want to put out debugging information. So can we do interior? All right, let's give it a try. Maybe done in record time here. Interior. Not record time. I guess it's been an hour 45 minutes. Okay, so now it's giving us crap about our termination of the depth first search. It says you made the queue longer. How dare you? Okay, so it found the one cube of air and the right set of values. So let's fire it up. Yeah, that huge set was not very helpful. All right. Hurrah. I think that's our best so far for part 2. Best for part 1 too. All right. Well, what can we do? We didn't end up writing a lot of specifications. We just sort of hand waved a lot. So it'd be better if we could be better if we could prove DFS's termination, or if we could add the properties to neighbors of that we thought it has. Um, let's see. So for DFS, what we want to prove is that we're adding something to the visiting set each time, and that can only happen finally many times. So one way to do that is to keep both a set and a list. But I think that would still be problems of, like, have both problems here. We've got a filter, and we have to say that, I guess we can say that. Right? We can say that the visited list is the set is the from list of the visited list. All right, let me checkpoint this before we screw it up too badly. Day 7 to 18. It's such a pain because we're going to have to deal with the filter as well. Plus, we would still have to give it sort of a maximum size, which is sort of an artificial constraint. I guess I'm less motivated to do this because I know it can be done, and it's just going to be painful. Is there something I'm not less sure we could do? So this function at least has this function at least has the bounds the original search space as a set that we can have go to 0. Right? The termination is when size of two search is 0. So we could convert to a list and back, but even then we'd have to check it explicitly. I'm feeling particularly disenchanted today. 'Cause this was a list heavy day, a set heavy day. Like all points, we could show that every point is in bounds, but it doesn't know dot dot, so you'd have to pull in our existing spec, our replacement that I wrote in a previous day. I know. Let's work on proving maximums. Don't remember what the panic was. Let's try this out on the let's try this out in the live demo. I don't think I've shown this before. So there's a live Liquid Haskell demo. Cyclic type alias definition. All right, I think I'm going to have to report this as a bug. So what it's trying to do is define our own maximum function in a place where we can apply Haskell reflection over liquid Haskell reflection to it. And then we could write, I'll make this bigger. Then we can't really have a type A that's, A is larger than everything in excess. But what we can have is a specification that says if X is a member of the list, then the maximum of excess of the list is greater than or equal to X. And that would use this definition of maximum. What happens if I get rid of this? Okay, that's better. So let's try that. Maybe we don't need it. So we need to find member. Member. So we need equal to define that. So there's nothing in the empty list. If x equals y, then true, else member x, y's. All right, so there's our okay. It still doesn't like that we've got member there. Can we inline it? No, I don't. No, that's not gonna work. It's gonna crash. Um. So I guess this is the part I don't understand is to prove things about these functions. Okay. And we need to reflect them. Okay. Yeah. Reflect. Okay. So yeah, we didn't get lucky, and it just worked. So we're going to prove this by cases, and so it's going to reflect the structure of both our recursions, hopefully simultaneously. So if we've got an empty list, then the theorem should hold. And otherwise, so if we get lucky, we just have to tell them All right, we didn't get lucky. It didn't like either of our cases. Okay, so we're going to tell it, we're going to use triple equal, which is not like JavaScript. It is checked equality. It comes from the proof combinator library. So we're going to say member is false, which is all we need because false can apply everything. Okay, great. I really thought the recursive case would work correctly. All right. So we need. So we'll ask it to show that y is greater than the maximum of excess. Wow. I can't tell. Seems to be multiple things going wrong there. Ah. All right, so there's a cute thing they do of like just say this follows. We can also say admit. Okay, so it doesn't think. All right. Okay, so if y equals x, then y is a member. All right, what I want to say in English is if y equals x, then y is a member of the list, obviously, and um, the maximum of the list is equal to either the maximum of the rest of the list or to y itself. So if y is greater than x, then okay. I don't think it still doesn't like my proof here. Oh, it's because it's the wrong order. I'm not sure this is true though. Okay. Great. So it accepted our reasoning there. And so now we just got the recursive case. Oh, no, didn't like that. I may have jumped ahead. All right, so what we have is the maximum is member y implies maximum is greater than y. And what we need is to apply that to the whole list. Right, so we need to tell it that this is true because member yxs is the same as member yxxs. So the thing I don't like about the proof combinator library is I keep wanting to say some unrelated facts, some more than one equality. And that doesn't seem to be what it's set up for. Like you can chain the equals together. You can add some fact to a proof term. So that's sort of what I've been using it for. But it seems more like inserting lemmas. Um, So I put in a couple other things I think are true. Hmm. Couldn't match expected type A with actual type B. So example proofs always look so nice and clean. Like you just set up the recursion and it figures everything out for you. Like that. All right, so we've got a proof about this. We got a proof of this, and we want to, okay, so helps to write out exactly what we've got. Right, and so what we need is can we use and? Right, so this was so this should be exactly equal to this. And this should be greater than equal to this, which is greater than equal to y. So did we do it? No, it. I've looked at their example a couple times and it just doesn't seem to work the way I want it to work. Combining proof certificates. So I'm going to try the triple and, except these are not proof certificates. Where are they? They are. Okay. No, they're type A rather than. So we might need to break that into a case. No, base Haskell is still complaining about types. Actual type. Oh, that was. That didn't seem to help, but it did pass. Yeah, the frustrating thing is here is I don't know. I don't know how to structure the proof and how much is that and how much is I don't know what the proof requires. So can we write this in a more equational way? It doesn't seem like just the one equation is going to do it. Okay. So here's one a legit problem with the proof is maximum is specified only on non-empty lists, and I haven't proven that this is non-empty. So let's add another case. Uh, so can I write it as just we didn't match that. Okay, so prove that case. No, not. It says it doesn't believe this is false. All right, so member Y, so it's member. All right, I just spelled it out. Right, that reduces to that, which is false. Okay. So can we do something here too? So if Y is a member, then something else, something else. This feels like I'm going down the wrong path, but All right, so we need to fill in these two cases. So this case should be obvious. It does not agree. If it's false, then this implication is true. Oh, member equals member. We proved it around about the wrong thing. Member Y. Okay. So we still got the difficult recursion case. Okay, so we have member X. Maximum X if X is greater than Y. No, it doesn't like that either. Okay, so let's unpack this. So the truth value of that is the same as x greater than equal y, or maximum xs greater than y. Okay. Let's work on just that case. So the maximum of x and xs equals how closely do we need to match? At some point we actually have to use our induction hypothesis here. Okay, so this is greater than maximum excess. Which is true by our inductive hypothesis. I think I keep getting the question mark in the wrong order. Okay. So otherwise is equal to maximum excess and by our all right, we got there. So this can probably be simplified now that it is true. But what this gives us is now if we use maximum in our code, we can use this proof. So for example, today we wanted to prove if we wanted to prove that where did we use it? I guess it's not particularly useful there. But this is a fact about the operation of maximum, and we can now use in areas where we might need it. So if we've got a list and we need to show that every element of the list is bounded by that max, we can pull in this as a function. And we do so, this is a function that returns nothing. We do it in a let or something like that. And then Haskell just simply wouldn't execute this function, which is good because this function does everything that maximum and member does, which we don't need to do again. All we need is the type. But I'm not sure whether we have to have a reflection on to use this type. And so I'll work on simplifying this proof later. But thanks for sticking up with me and staying up with me, I mean. And we did manage to write our proof, even if it has only limited relevance to today's exercise. Thanks. Good night.